Now let's discuss lines in space. So we want to find the equation of this line. So we're going to need two things. We're going to need a point on the line. Let's call this a point. Let's say PO. That's a point on the line, which will have the coordinates XO, YO, ZO. We also need the direction vector. Now we want the line to be parallel to this vector V. Let's say the vector V has components some A comma B comma C, and we'll call this our direction vector. Now we know two vectors are parallel as long as one vector is a scalar multiple of the other. So let's suppose I find another point on the line, so I can create a vector from here to here. Let's say this point has the coordinates x1, or let's just call it x, y, and z. So this vector that I just created, it's going to be parallel to the vector v, direction vector. So we can say that the vector from PO to P, it's going to be a scalar multiple of vector v. So let's say T is a scalar multiple, and this is vector v. Now, how do I get this vector PO to P? Well, we take its final point, subtract the initial point. So if this is the final point, that's the initial point, we can find the vector. So let's put this down here. So the vector from PO to P, it's going to be x minus xo, y minus yo, and z minus zo. So that'll be the vector from PO to P. And we know this is going to be a scalar multiple T. T is just any real number. So we can say that right here. T is any real number. And T times the direction vector, which has the component A, B, and C. And now with further distributions, you can also say that this is the vector x minus xo, y minus yo, z minus zo is equal to A times T, B times T, and C times T. So that's your vector equation of a line. Now this is written in terms of a parametric form, so you can also equate their coefficients. So here's the x component equated with that, y component equated with that, and z component with that. So we have x minus xo is equal to at. In other words, if you solve for x, you'll have x is equals to xo plus a times t. So that's our parametric equation for the x value. For the y, we have y minus yo is equal to b times t. In other words, you can solve for y, you get yo plus b times t. And the z component is z minus zo is equal to c times t. So if you solve for z, you'll have, to solve for z, you get z is equal to zo plus ct. You have your direction and a point on the line, xo, yo, zo. So these are called the parametric equations of the line. So another type of equation you can also write for an equation of a line in space is a vector equation of a line. So the vector equation of a line, it's written in the following form. So think of creating a position vector. So from the origin to this point, PO. So let's call this our position vector. Let's call it RO. So that vector is computed by taking PO minus the origin. So you'll have your vector RO, which is simply the vector with component XO, YO, ZO. So again, you take the origin and then you subtract the final point, that's PO, you get this vector. Now we have the direction vector, which is computed from PO to P, which is another arbitrary point on the line. So that's this vector, which is parallel to this vector. Now, if you want to use vector addition to find equation of this vector right here, so this will be the vector R. So vector R is just the sum of this and that. So we can say R is the vector, which is RO using vector addition, plus that vector, which is PO to P, which is our direction vector. Now, since that vector is parallel to the vector V, we can say that this vector PO to P is some scalar times vector V. So I can simply substitute that in here since they're parallel and I have a vector equation of a line. So R, let's call it a function of T, is equal to RO, which is my, you can think of it as your position vector, plus times T, plus T times the direction vector V. So you have your position vector right here, which is a point on the line, but create that vector from the origin, plus some scalar right here. This is your scalar, and this is your direction. So this is another way you can represent equation of a line in space. If you're to expand this is how it's going to look like. So R of T, just the equation of the line in space, this is going to be RO, which will have the components XO, YO, ZO, plus T times the direction, which is A, B, C. That's the component of a direction vector. Now, since R of T is any point in space, so you can just call it any point on the line in space, you can also rewrite this as X, Y, and Z, and this is equal to the right-hand side, so it will always equal to this. So this is another way you can also interpret equation of a line in space. This would be the vector form of a line. Now, I usually like to use this one, but you can also rewrite this in parametric form. For instance, if you, again, redistribute the T and equate the coefficients, you'll get the parametric form, which will be X equals XO plus AT, Y equals YO plus BT, and Z equals ZO plus CT. So that'll be the parametric form of the same line. And of course, T, we can say that it's just any real number. Here's an example to illustrate. Let's find the line through these 2 points. So we need the direction. So we need the direction vector. Let's create a vector from P to Q. So our V, it's going to be the direction vector from P to Q. So we take Q, subtract its coordinates from P. So this will give us 1 minus 1, that's 0. And then 1 minus 2, that's 1. -1, and then -1 minus 0, that's -1. That's our direction vector. So this is your direction vector, direction of the line. Now we also need RO, which is our position vector. Now, since we're going from P to Q, we're going to use this as our point PO to create that position vector. So we take this, subtract from the origin, you get the vector 1, 2, 0. So your vector equation of the line, R of T, is simply RO plus T times the direction vector. Let's substitute them. So this will be equal to 1, 2, 0 plus T times the vector V, which has the component 0, -1, -1. So this is your R of T. This is the vector equation of the line. Now, if you want to write the parametric equation of the same line, all you got to do is write X is equal to XO, that's 1 plus 0T, so it's just 1. And then Y is going to be 2 plus -1 times T, so that would be 2 plus -T. And Z would have, again, ZO, that's 0, -T. So that would be the parametric form of that same line. Another example, let's find the equation of the line through the origin parallel to this vector. So that means our vector, the direction vector, will be the direction of this vector. So it has X component 0, Y component, the J, that will be 2, and K will give us the Z component 1. That's our direction vector. We wanted to go through the origin, so your point, your position vector R0 is just going to be 0, 0, 0. So therefore, our R of T is going to have the component 0, 0, 0 plus T times the direction vector 0, 2, 1. So that will be the vector equation of this line. And the parametric equation would be X equals 0 plus 0T, so that's just 0. Y equals 0 plus 2T, so that's 2T. And Z equals 0 plus 1T, so it's just T. So that'll be the parametric equation of this line. Here's our last examples. We want a line through this point. So we're going to make that a position vector and perpendicular to this plane. So that means we're going to take the normal of this plane. Now, if you're not sure what a normal of a plane is, so here's a plane. The normal is a vector that's always perpendicular to the plane. So it's going this way. That's the normal vector. So the normal vector of this plane is these coefficients that we have, 3, 7, -5. So our normal vector of this plane would be 3, 7, -5. So for the line, this will play as a direction vector. So we want a line also parallel to that. So, and it'll be perpendicular. So imagine the line looks like this. So we want the line perpendicular to the plane. So that means it's going to be parallel to its normal. So we want a line like this, passing through that point 2, 4, 6. So the picture is off scale, but that's the line you want. It's parallel to its normal. It's perpendicular to the line. So our line L will have the equation R of t is equal to RO. So we're going to make our point a position vector. So you can think of RO will be the vector 2, 4, 5. We take that point, subtract it from the origin. So this will be 2, 4, 5 plus t times, again, the normal will play as a direction. So this will be 3, 7, -5. So that will be the vector form of the line. And the parametric form will be x equals 2 plus 3t, y equals 4 plus 7t, and z equals 5 minus 5t. And of course, t is going to go from all real numbers. So these are the two different ways you can express an equation of a line. There's also a symmetric equation of a line. So you can look that up as well.